Again, it's not 0.4 to 0.8. Generically, you're writing these expressions for any interval. Any interval, the 7th interval, the 9th interval, the 12th interval. How do you express the coordinates of those points? And then how do you piece together A to get that y coordinate of that for the current value of x in that interval?
What's the red point? I think
it's like it is the point for the current value of x, right?
Okay.
And so by writing the y coordinate of that current value, you're essentially writing this whole function. Does that make sense? By writing the y coordinate of the red point, you're writing the coordinates of all of them.
Okay, but that's our current x. Is that what you're saying, the red one? Or is it just an example?
It's just an example. So I could have made it here. I could have made it here, and it would be the same. So we're creating the function, thinking of it as just any typical point along the way. Does it help?
Yeah.
So let's try how about the coordinates of the points? Where's Daphne? Bitches. Daphne, did you get the coordinates of the first point? She wants left x, comma, f of left x. Is it right? Yep. And that's because it's left x. It could be in any interval. Left x automatically gives us the left side of the current interval. So it works for all the intervals. Yep. Left x, f of left x. Okay. Good job. What about where is Lester? Thank you. What about Ethan Eisner? Is Ethan here? What about Mackenzie? Is Mackenzie here? Okay, Jaslyn Jarman. Okay. Okay, the x coordinate is? Good. So left of x plus, then we're going to go across the interval, plus delta x, right? So left of x takes us to there, and then plus another delta x gets us that x coordinate, and then the y coordinate is f of that. You're going to take that x coordinate, left of x plus delta x. F of that will be its y coordinate. So we got the two coordinates of those 2 points. What is something we're going to need to build the a function to get that y coordinate? Just anything. What's something we're going to need? Where is Hue Wang? Last name Wang. Yeah. So did you get any part of this ax function? What's one piece that we're going to need for that ax function? What's that? A of left of x? No, not quite. How about, where's Alicia? M, Manice. Yeah. So what's one aspect or part or component of that ax function, that y coordinate? Any idea? Nothing about it. You can't tell me anything about it. Volunteer, yes, sir. Right, we need the constant rate for the current interval, right? So we need the constant rate for the current interval. How am I going to set up the constant rate? Where's Michael Alvarado? Michael. Okay. Where's Petrie Griffin? Or Griffin Petrie? Griffin, tell me about the constant rate for this interval. Good. F of left x plus delta x, the final y, right? Minus initial y, which is f of, and then you can just do over h, because that's what delta x is. Change in y over change in x. That's going to be part of the ax, but we're going to need that constant rate to get that y coordinate, build this function. Yes, sir?
This delta x is not dx, it's h.
Yeah, H, right, so I should have been consistent. So let's make it all H's. Good. They're the same, but we'll just use the same symbol. So we'll do left of x plus H minus left of x all over H. Yes, that's the same as delta x. Okay, so what about the general structure of that a sub x function, or that y coordinate? The overall structure, to build that, where's Mashabir? Hussein? Not here. Okay, where's Ian? How about the overall structure of the y coordinate? So this is like, right, what? This is like x initial, y initial, and this is like x final, y final. So what's going to be, how are we going to get y final? You just made my day. Y initial plus the change in y. But that's not a full delta y because it's just partially into the interval. So that's the general structure of this y coordinate. It's going to be the y initial, this y coordinate of this, plus how much y changed to get to the current x. Can you take it from there? You've got the rate. So the question is, what is y initial in terms of x? What is dy in terms of x? We know the rates involved. So what is y initial, and how do you calculate dy? See if you can finish, if you didn't already. Go. Yeah. Dx, remember, is how x changes. No, dx is how much it's changed in the current interval, right? Dx is a changing value. Delta x, or h, is the right. So dx right now the way I'm showing it is from here to there. That's dx, but that's changing, continually changing. No, we're calculating the rate. We don't know the coordinates of this point. We're getting this rate of change, which is based on the segment that extends from here to here. That gets us the constant rate. We don't know. We're trying to find the coordinates of this point. So that constant rate is based on those two. Okay, where's Justin? Bilibos. Justin. How'd it go? Can you tell me, can you just tell me what y initial is? How about y initial? Do you know what that is? Nice and loud. Not sure? Okay. How about Yash? Yash Shaw. Is Yash here? Vinay Chand. Vinay Chand. How about y initial?
Would it be 0.4?
No, it could be any interval. So we could be in any interval. So how do we express y initial for any interval?
And left of x.
Uses left of x is the x coordinate, so the y coordinate would be
F of left.
f of left. We got there eventually. Y initial, you should have f of left of x. Cool. All right, how about Chen, Zhao? Where's Chen? Did you get dy? How are we going to get dy for this? Not sure. You want to do it? No, because dy is going to be, so we have y initial plus the change in y. Here's dy right here, from here to here. How do we calculate dy? Volunteer, yes sir. Dy is the same as the rate? Or are you going to keep going? Right, it's rate times dx. And so the rate is r of x. And how do we express dx now? That's it. How'd you do? Now, R of x, we would rewrite that expression up at the top, but for clarity's sake, I'm just going to write R of x. But we would that ratio up there would go where Rx is. And that's y initial plus dy calculated by m dx. And that gives us the y coordinate of any arbitrary point on the approximate accumulation. So it's the function. That's the function. I think I have that here somewhere. There it is. Okay, is that what we said? I just changed the order. I did dy plus initial y. dy plus initial y. So that is our approximate accumulation function. Notice it's totally different than the long summation notation we got when we started with rate, right? We started with rate and we went towards accumulation. The ax function was a totally different function, right? Based on summing up little bits of change. This is different. This is based on y final is y initial plus the change in y. Okay? So it's a whole different function now that we're taking the reverse process. Okay, what is the next question on your sheet? Okay, so we want to sketch R, and now we actually want to compute values. Maybe split up the work with the people around you, so you don't compute all three constant rates. Maybe so everyone computes one, and then share the knowledge. So just pick either. So you've got three constant rates, but we don't want to just eyeball. We want to actually get a decent, or get the exact value. So with those around you, determine if you're going to find constant rate number 1, or constant rate number 2, or constant rate number 3, and everyone just do one, and then share once you get your answer. So fine, we're creating the approximate rate function now out of these three constant rates. Work together. Go. Yeah, sure. X is our approximate accumulation function. Yeah, the reverse process. We just built it out of F, right? So we have an exact accumulation. And so using F, right? So A of X is based on left, right? It's F of left of X and F of left. Using the F function, we just built the approximate accumulation. And so it's trying to be like the curve, but it's based on constant rates. And that's what we want. So now we can do an approximate rate function with those constant rates. Yes. Right? Exact accumulation to approximate accumulation to approximate rate to exact rate. Anybody get M1? You found the approximate rate for the first interval? Anyone got it? Tell me. 0.268. Somebody else get that? You did? No. Do we know what we're doing? What's that? Yeah, I don't think it's 0.2. Yeah, you got something? What'd you get?
0.67.
Yeah, that sounds better. 0.67. How do you find that? How do you find this first constant rate? What are we going to need to find that constant rate? It's going to be the change in y over the change in x. So we need y final. Now this is the now we're not thinking arbitrarily. We're working on the first interval. So we are ending at x equals 0.4, and we're starting at x equals 0. So you're actually calculating that rate of change. And so you should get, I heard 0.67. Does somebody else get that? How about the second interval? Who got a value for the second interval? Yes, ma'am. 4.75. It looks right to me. Somebody else get that? Change in y over change in x. And how are you going to get the change in y? You're going to use f, right? You're going to use f to get y values of your endpoints. Change in y is the difference of the y values of the endpoints. Change in x is always 0.4. Third interval. Anyone get a value for the third interval? Yes, sir. 12.73. So you're using the function to get the y values, and then you're computing change in y over change in x for each interval. Does it make sense? Who said no? How do we calculate a constant rate of change? So how do we calculate a constant rate of change? Can you tell me?
Oh, sorry.
Yeah, it's okay. Just
dy over dx.
right. In this case, but so the only information we have to get these are at the endpoints. So we can solve delta y over delta x. So delta y is going to be y final minus y initial over x final over x initial. Delta y over delta x.
I guess what I'm getting confused is, are we making up points or are we
No.
actually using
No, we're using these. We know where that interval starts. It starts at 0.4 and it ends at 0.8. If we're keeping h at 0.4, then we know exactly where that interval starts and stops. So how do we get y final and then y initial? Y final is the same thing as f of what? Not like. It is. F of 0.8. And then y initial is f of 0.4. The y coordinate on the curve. See, it's at these endpoints that we have information because they're the same points as on the curve that we know, the function. All these points in the middle we don't know. But we know these points at the endpoints because they're intersecting the curve, which we have the function for, so we can get those y values. Is it better?
I think so, yeah. I mean, yeah, I get it now.
Yes. F of 0.8 minus f of 0.4 over h, which is 0.4. Other questions? Very good. Okay. So what is the rate function? That's your next question. What is this? How can we write a general form for what I'm calling R1, the rate function, the approximate rate function? Let's see here. Where's Tyler? Tyler here? Randette? Who said yes? No Tyler Randette? Or Randette? Camilla? Tybowski? Yes? How about the rate function? I want to write, just like I wrote the A function up there, I want to write a general form for the whole approximate rate function. What would that be? Okay. Any volunteers? Yes, ma'am. R of left x. R of left x. What's R? Actually, R is what I'm asking you to define. What is R? I'm asking you to define what R is. Hector.
Would it just be the rate function right there?
Yeah, we already did it. We already did the rate function. It's part of the A function. It's that. We already did it in the first parentheses there. Right? So that, because that works for any interval. F of left x plus h minus f of left x over h. We already did it to build that A function. That's your rate function. Yes, yes, sir.
For since R sub 1 of x, is that requiring
It's everything. So R sub 1 of x is this whole step function. When x is 0.2, you're going to get 0.67. When x is 0.713, you're going to get 4.75. When x is, when x is here at 1.03, you're going to get 12.73 from that function. Okay, so what's our goal? Exact rate of change. And what's the key to getting from this approximate rate of change to exact rate of change? Where's Brady Lorenz? Brady here? How are we going to, so what's our key idea here to get from approximate rate to exact rate? What do we do next?
using the integral?
What's that?
Using the integral?
No, not the integral. The integral gets us exact accumulation, but just how are we going to proceed to move towards exact rate of change? Yes, ma'am? We're going to make the interval smaller, so let's watch it. Ready? Right now, h is 0.4. Here's h.28. So what happens? The approximate accumulation function gets better, and then we get more steps. Here's h is 0.16. So look, that rate function is beginning to take form, right? That rate function is beginning to take form. So let's make h really small. You can't really even see that there's steps anymore, right? So this is the same thing we saw before. When h is really small, small enough, we essentially get the exact rate function. Okay, so what is that exact rate function? It's the same. It's the approximate rate function for a sufficiently small h. For sufficiently small h. And so one way to express that is what we call a limit. We write this notation, the limit as h approaches 0, which means really super small h, sufficiently small so that it makes no difference anymore between approximate and exact. So it's going to be the limit as h approaches 0 of that whole thing. So I don't want to rewrite it all. So if I take the limit as h approaches 0 of our approximate rate function, I get the exact rate function. So in the forward process, we just had the integral sign, and the integral sign included the meaning limit as delta x gets really small. Here in the reverse process, we actually write out the limit as h approaches 0. Okay, any questions on this? So this right here was like an exact reversal, literal reversal of what we did the last 5 weeks. And so it's good to review all those tools and put those tools back to work and see how it works in the reverse process. But, here's a big but. Everyone listening? But, we don't use this approach to now continue on from here in our endeavor. Our endeavor is, you know how much of it you have, you want to know how fast it's changing. To actually make forward progress from here, we're going to start over with a different approach to this, and that's in the bottom of your page is what's called approach 2. Okay, so very good to investigate the reverse process exactly how we did it in the forward process. That's what we just finished. But to go on from here, we're going to look at a new approach. So let me show you that, and we'll call that approach number 2. And so, I gotta make h 4. Sorry, I got to make h 0.4 again. H is back to 0.4. And so let's take a look at what this is about. So this is, again, this is what we just did. Intervals of 0.4 that we set ahead of time, and then x increases through those intervals, and it maps out the approximate accumulation function that we did. So here is the blue is now the new approach that we're going to take. So notice this blue bracket, or this blue brace, instead of setting all the intervals at 0.4, at increments of 0.4, we're going to let the interval 0.4 be a roving interval along with x. So what happens? The value of x is always the left side of the interval, no matter what x is. So that interval roves along with it. So this is how we're going to do the reverse process. This is called approach 2. Approach 2, okay? So what's your first question? So I'm going to take off the old way, and so we're just going to starting to look at the new way here. Approach 2. Remove the old approximate accumulation function, just looking at that. And so then for any given value of x, we want to calculate a rate of change. We're going to calculate a rate of change, and we're going to visualize that rate of change as what we call a secant line, okay? So it's like instead of having those fixed constant rates, now we have this continually changing constant rate. And that blue line we're calling a secant line. A secant line. Okay? Okay, so answer question A. 2A. Answer question A, 2A. And then talk a little bit about that. Can you see it? No. Okay, where is Alejandro Ruiz? Alejandro. Okay, Jacob Janowski. Where's Jacob? Okay, you lose attendance points if you don't answer. Brandon Chavez. Brandon. Tell me, are we going to get these rates of change from the secant line? Are they going to be constant rates that change abruptly like we saw before? What do you think, yes or no?
Yes.
Okay.
They're always changing, like how much it's going to.
So remember before, so we had a constant rate, and then all of a sudden at 0.4, the constant rate abruptly changed to a different constant rate. And then at 0.8, suddenly the constant rate changes to a different rate. That gives us the steps, right? Is that going to be the case now in this new way of looking? Are you going to get constant rates that change abruptly at certain values? Okay, so if not, what will we get instead? What are we going to get instead if we don't get constant rates that change abruptly? Where is Montarius? Okay, thank you. Summer G. Gutierrez. Summer. What will we get instead for the rates of change? Okay. Not quite. Any volunteer? What do you think? Hector, is that?
No, it's correct.
Oh, just scratching. Okay. Anyone, can you describe what this rate function will look like from, like, if we were to have a function of all the rates based on the secant line as x increases?
It's gonna be like a smooth function, right?
Smooth function, right? Exactly. Let's see it. So we don't get the step function, right? We don't get the summation. We're going to get a smooth function because as soon as x changes a little bit, the rate changes slightly too. So we don't get these abrupt changes in rate. So here's the million-dollar question. Is this, so with h is 0.4, is the new rate function that we have now, is it approximate or exact, and why? I want you to talk about this. Is that an approximate rate function that's being sketched out over there based on the secant line? Or is it an exact function, approximate or exact? Talk about it. Go. Okay, so let's just see by show of hands. How many concluded this was approximate rate of change? How many concluded it's exact rate of change? We've got to fight. All right. So let's look at a particular value and confirm or deny this. Let's see which camp wins. So we're going to look at x equals 0.55. We're going to look at x equals 0.55. And so let's go back and think about in the first couple weeks of the course. I'm just going to turn off everything except, let's see here. I don't know what do I want here? That's what I want. Okay, so at x equals 0.55, how could we get a very good estimate of the rate of change at that moment? Do you remember doing this? I want to get a very good estimate of the rate of change at the moment x equals 0.55. When we did this at the beginning, near the beginning of the course, we were just talking about rate of change in general. Rate of change in general. So what should I do? Let's see. Do you remember? Where is Trevor Hoke? Where's Trevor? Yeah, so I want to get, for this value at x, current value of x of 0.55, I want to get a really good estimate for the current rate of change at this moment. How can I approach that to do that? Remember what we... So this was more kind of a process that we looked at to get that. Yeah? He wants to zoom in really close until we get a linear... Remember doing that? Yeah, exactly right. Good job. So we're going to zoom into there. Close enough. I want to zoom in. Does it look linear yet? How about now? Not quite? We'll do one more just to be sure. Okay, here we are. So what are we going to do? So we know that if we have a small enough moment, that curves are essentially linear, and that means that we have a rate of change in a moment. Rate of change in a moment. So what do? We pick off some values, right? So here is let's do 0.535 and, I'll use this. Write this down. Ready? Everyone write this down? 0.535 and 0.641. 0.535, 0.641. And the other point is? Do 0.545, 0.678. So at 0.545 is 0.678. Find a good estimate for the rate of change at the moment, 0.55. Everyone go. Everyone should be able to do this. Find a good estimate. Compare with the people around you. What was the first y value? What was the first y value? And how far are we going over? 0.01? Did you get that? 3.7? I got 3.7. Did you get 3.7? 3.7. So let's plot that point. Over here on our rate graph, let's plot that point. We'll plot it red for exact. Okay, so our rate graph's over there. We just plotted the point of 0.55 and our very good estimate for the rate of 3.7. Let me zoom back out. Now what I want you to do is find that rate according to the secant line. X is 0.55. Everyone should be able to do this. Confident? I want you to find the rate that the secant line is indicating. What is the rate of change that the secant line is indicating? Go. All you need to know is this is 0.55. It's the same volume function. You still have f of x is the same function as before. H is still 0.4. Can you find the rate of change indicated by the secant line? The rate of change indicated by the secant line at 0.55? I hope so. I really got my faith in you. What's the x value here? .1. Oh, this is 0.55. What is it? What do we need? Change in y over change in x. So, where's Preston Wise? Preston. Preston, are you here? Too many missing. Nicholas Avalos. How'd it go? How did you find the rate of change as indicated by the secant line? What did you tell me your process? Okay. So I'm not sure why you're referring to left x. We've got all the values, right? We've got all the values we need. Okay. So what is this rate of change? We'll call it m. How do we go about that? Where is Adrian Hernandez? Adrian Hernandez. Yes, sir.
Okay, so at 0.55, we can plug into the equation over the corresponding y value,
Right.
which I got at 0.69.
Point 69. Cool. Okay.
And then we have to do, so then we'll take 0.55 plus 0.4 to get x at 0.95.
But how do you calculate the rate of change? Why do you have to add? Oh, I see. I see. Okay. To get the 0.95, right? Okay. Sorry. Right.
3.59 as my y value.
Right.
So I take 3.59 minus 0.69 divided by 0.4.
Right. Change in y over change in x. So we use the function to get the y values, and then we do change in y over the change in x. Moment of truth. What'd you guys get? 7.2? 7.23? Uh-oh. Does the secant line, what's indicated by this is the secant line, does it give exact or approximate rate of change? How many people say approximate? How many people say exact? What about the rest of you? Not sure. Well, we just showed. So we got a really good estimate by zooming in. Here we go. Come on. Let me zoom in with both of them showing, okay? Hold on. Shh. Now I'm zoomed in with both of them showing. We got the local linearity on the actual function, and then we have our secant line. Is the secant line giving us the exact rate of change? No, it's a higher or lower rate of change. The secant line in this case is giving us a higher rate of change, right? It's giving us more of a change in y for the change in x, same change in x, or resulting kind of a steeper line, right? And that's why when you did it according to the secant line, you got this much higher rate of change compared to what we found was exact, or very close to exact, based on just looking at the local linearity of the curve. Okay, so let's go back. And let's sketch where we were before. We had so this blue curve is the rate of change function from the secant line. That red point is one particular point of exact rate of change that we found at 0.55. So do you see why that secant line is, just because it's a continuous curve doesn't mean it's giving us exact rate of change. Do you see why it's giving us approximate rate of change? Why? Because for this particular function, it's always showing a rate of change that's greater than the actual rate of change at that left point of the interval. Okay, so let me just show you what the exact looks like. So the red one, let's put the beans there. Look at that. Okay, so the red curve is our exact rate of change. The blue one, based on the blue secant line, is our approximate rate of change. So what we want to do now is we want to write, I'm going to pause this over here. Can we write, and I'm going to call this R2. R2 for approximate rate of change in approach 2. And now we want to write a general formula for R2, and this is easier. It should be, this is easier. Can you write a general formula for R2 of x? The approximate rate of change based on the blue secant line. We want to write a general formula now for the rate of change. So if it's a rate of change function, the general structure of it will be what? What will the general structure be of the function? How do we calculate rate of change? Change in y over change in x. That'll be the general form structure of that function. And you're going to do it based on the secant line. You're going to get the change in y. Now, for any x, right? For any x, that gives us the function then. So not for 0.55 anymore, for any x. Can you find R2 of x? Go. This is question D. Question D. Show me. Let's see. Start over. How do we write the rate of change of that blue line for any value of x? That's what we're doing. Given that this is any x, you write the rate of change of that blue line. Where's Bo? All right, let's regroup. Where's Bo Wan? Where's Bo? No Bo? Melissa Walls. Melissa, was your first instinct to find the coordinates of those 2 points? I hope your first instinct was to find the coordinates of these 2 points. Yeah. Okay, so what was the coordinate of the first point? What are the coordinates of this point down here? X and f of x. Why don't we need left x anymore? X is always the left side of the interval. We just use x. We don't need left x anymore because with this roving interval, x is always the left side of the current interval. So we don't need left x. And this is kind of this is the key to why we want approach 2. Left x is too cumbersome when we get to the exact rate function. We want to get rid of that left x, and this does it, okay? How about the coordinates of the other point? Where is Tan Yu, Zhang? Tan Yu? Okay, how about Farah? You're up. What are the coordinates of the second point? X plus? What are we calling the change in x now? H. And? F of x plus h. So this is a lot cleaner, right? A lot easier without that left x in there. So now we're ready to write the function for the rate of change. Tell me what it is. Where's Muhammad Al-Balan? Okay, how about Angela Yao? Angela here? Yeah. So we're ready to write the function R2 of x. Tell me. Are you Angela? Yeah. So we're writing the rate of change of this blue line. We got the 2 points. How are we going to get the rate of change? What What is that? Right? F of x plus h minus f of x. Change in y. And what's the change in x? Just h. Don't pack up, folks. There it is. Yeah, don't. Yep. This is a lot cleaner version than R1. Remember R1 involved, this is our approximate rate function. Our approximate rate function with the roving interval. With the roving interval. It gives the blue curve. It gives that blue curve over there. So, again, what is our goal? Exact rate of change. How are we going to get exact rate? Where's Summer? Oh, twice in the same day. Summer, how are we going to, from here, how are we going to get exact rate of change now from this new approximate rate function? What's the general idea to do that? Don't check out on me, folks, please. Nope, we've got the approximate rate. How are we going to get the exact rate function or move towards it anyway? Carl, where's Carl? Heinz. Carl.
Make h smaller.
Yeah, so it's a roving interval. We can still choose to make it smaller. So let's take a look what happens. I'm going to make h smaller. So now that the h is smaller, we've got a smaller roving interval. And notice the secant line is hugging the curve more because it's a smaller interval. I'll make h even smaller. Watch, ready? So here's h of 0.11. Now what about the approximate versus the exact rate of change with this much smaller interval? Do you see that now we're much, much closer? Do you see that? You can't even see any daylight between them now. Let me zoom in on that. Come on. Okay? Still not exact, but a lot closer, right, for a smaller h. We'll make h smaller again. Here's h of 0.02. The rate, so because that second point is so much closer, the secant line is doing a really good job of estimating the current, the rate at the moment. And what you notice the blue curve over there is converging on the exact. So here is h of 0.005. Can't tell the difference, right? Can't tell the difference for h equals 0.005. So again, exact rate of change is going to be this rate function just wrote, but for sufficiently small h. So this is exact rate of change when h is sufficiently small. So there's kind of actually two ways to express that. We talked about the limit as h goes to 0, and then there's another way. When you see this also means the same thing. Essentially 0. Essentially 0. We can't make h equal to 0. Why not? It's a problem. You can't divide by 0, right? You can't divide by 0. But, so this means essentially small enough so there's no difference, right? Small enough so it's essentially 0. So that's one way to express that. And then we talked about that notation also. Those mean the same thing. Those indicate the same thing. Make h really small to get the exact rate function. Okay, we'll be back on the regular cycle. Written homework due Tuesday. In front of that. In front of that. Yeah, you want to rate this, yeah. Could write that after.
After, with a
comma?
Yeah, sure.
So this one is the approximate, so we have to find
No, it is exact when h is small enough. So it's both. So that formula up there ends up being both. It's approximate when h is large, not small. And then when h is essentially 0, it's exact. So it'll represent both for us.